but I do want to take some time to make sure we clear some of those things up because we will be using these 6-2 tools as we go along. Really, from this point on, our types of problems are going to break into two categories. One of those categories is going to be binomial distributions, in which case we'll be using these tools. The other cases will be distributions of means, in which we'll be using our Chapter 7 tools. So these Chapter 6 tools are important for us to get comfortable with. So I would like to spend some time today kind of going over some of the questions that I've seen you guys talk about on the forums and anything else that kind of comes up that you guys want to ask about. It is certainly helpful for you guys to be as specific as you can if there are things that you're fighting with, so we can try to make sure we address those directly. But the forums are also a good place to bring those things up, because then I can see them and bring them here. But I'm always happy to look over stuff if you guys bring it up when we start class, so keep that in mind. So in speaking about binomials in general, there's a couple of things we should keep in mind. So pink, okay, I'll go with pink. So binomial distributions. So binomial distributions, the big thing about what classifies something as a binomial distribution is that there are two options. So it has to be a yes options, has to be essentially a yes or no situation, a positive, negative situation. So in this situation about, it's a made up situation about somebody forgetting lunch. The chance you forgot lunch each day is 37.9%. So it's either yes, you forgot lunch, or no, you didn't. So there's only two options in that scenario. So it is a binomial distribution. When we're doing binomial distributions, the variable we're looking at are x, if you will. Our variable is the number of times we get a yes. So we often say number of successes. Now, in this case, whether that's the successes of remembering to bring your lunch or a success of forgetting to bring your lunch, depending on which one you want to call success, we'll probably call, let's see, what are we told here? The chance of forgetting your lunch is 37%. So forgetting your lunch is going to be considered a yes. So that would be our number of successes. So that number of successes out of some number of trials. So the number of, in this case, days, but could be the number of flips of a coin, number of events, number of, of parts that we make, however many times we're looking at something happening. So out of those n trials, how many successes are we going to get? So if we're considering this to be over 40 days, that 40 is our n. And as we said over there, x is the number of successes here. Days that you forget your lunch. Forget your lunch is our yes. These are positive, so that's our x. Now, there are a couple of different things we can calculate with these. We can find a mean, just like we have been before. We usually refer to that mean like we did in Chapter 5 and 6.1 as an expected value. Expected value. Now, the trouble with mean, I think, in binomial distributions is we've got all these more complicated tools to do things, and you kind of want mean to be a complicated tool. But mean for binomial distributions, you do remember we're switching to this Greek mu because this is the mean of a population instead of a sample. It would be X bar if it's a sample. All probability distributions are populations. So the mean will always be mu. It still is our expected value. And if we forget our lunch 37.9% of the time, then we would expect to forget it 37.9% of the 40 days. So that's all we do for finding expected value for a binomial distribution. We take the number of trials, multiply it by the probability of success, and that's going to give us an expected value, a mu. So here it would be the 40 days times the 0.379. Do be sure that's in proportion probability notation, not as a percentage. And whatever that product ends up being, that's going to be our expected value of days we'll forget our lunch out of 40. So if I want to calculate that real quick, bring up my calculator here. 40 times the 0.379 is going to be 15.6. So 15.6. And this is days multiplied by a ratio. So this is 15.6 days. So the interpretation of that, a mean, that mu, we would expect to forget our lunch a little more than 15 days, about 15 and a half days out of every 40. Does that seem reasonable so far?
Yes, thank you.
Mm-hmm. Where the formula for standard deviation comes up is a little bit more dramatic. The nice thing is, I don't want to go too far into where it comes from, but you remember the standard deviation formula did always have a big square root in it. And the standard deviation formula had the mean in it and the deviation from that mean in it. So some of the pieces are the same, but that NPQ, the square root of that NPQ is going to give us that value for standard deviation. Because this is a probability distribution instead of a distribution of values, that standard deviation formula simplifies a tremendous amount. So instead of all that, sum of the x minus x bar squared divided by n minus 1's square root, we just get that square root of our NPQ. The NP is essentially our mean. That Q is looking at how much false we're going to get and looking at spread. So, where exactly that formula derives from is a little bit of a calculus problem. So we don't really go into where that comes from, but we can still use it like we normally do a standard deviation. So to find it, we're literally just going to take that square root of the 40 times our probability of success, our P, times our probability of failure, Q, which is just 1 minus 0.379. Your book even doesn't like going with Q. I think you're usually, when you see this in the book, it's usually the square root of n times P times 1 minus P. That 1 minus P is just what we're calling Q, just to give it a different label. So we multiply that out and we'll get a standard deviation. Again, I'm going to grab that calculator. Why don't I make sure that calculator is viewable for you guys, because we'll probably have some calculator questions later. So square root of 40 times the 0.379 times the quantity 1 minus 0.379. End that and get out of that radical. Didn't have to get out of the radical, but might as well. And we get a standard deviation of, oops, that's why I don't like that. It disappears on me. 3.0, I'm going to go 0.07. And again, one of the reasons that square root is there is this is, days, but we're multiplying those days by 2 probabilities, so that square root undoes those 2 probabilities, and this is still a standard deviation of 3.07 days. Now, what does that mean to us? Well, remember what standard deviation has always kind of meant. It's a sense of spread. So the middle is going to be the 15.6, but how spread out is that? Do we expect 15.5 days on average, plus or minus 1 day, plus or minus 2 or 3 days, plus or minus a week? This standard deviation gives us that sense of spread. So we will be 3.7 above and below that. So 18.67 down to, I don't want to have to do that math in my head, 12.53 days. That's going to be our within 1 standard deviation. So that's going to be our 60% or 68% of the time. We'll be only forgetting it between 12 and 18 days. 95% of the time will be that 15.6 plus 2 of those standard deviations. So that would be what, 21.74, I think, days. And 15.6 minus 2 times the 3.07, which is somewhere around 9-ish. So that's going to be our 95% of the time, according to our empirical rule. And anything outside of that is our unusual. We're not calling those outliers, but that's going to be our unusual. Remember, unusual is anything outside of 2 standard deviations. So the first number of days larger than the mean, so we're looking at this side, that would be considered unusual. Well, 21 days wouldn't be unusual because 21 days is less than that. 22 days is more than that. So 22 days would be the first unusual day, or unusual number of days. I'm going to go a little bit fast today just because I want to be able to talk about a lot of examples. But I do want you guys to stop me, because that's kind of the point of this, is for us to look at a whole bunch of things and get at what you guys are fighting with. So I want to look at a lot of problems, or not, don't have to look at a lot of problems, but I'm going to kind of go through them on the quicker side, expecting that you guys will stop me when I start saying stuff that's crazy or just weird, or where you have questions. Fair? Yes, Matt, we get
yes,
that.
thank you.
Okay, so the first number of days larger than that mean, that would be considered unusual. So if you forget your lunch 22 days or more, it would be unusual. Or if you forget it less than 9, it would be unusual. Find the probability of forgetting your lunch at least. This is the dreaded at least that everybody's been fighting with, and not unreasonably, but we do want to get comfortable with that at least. So what's the probability of forgetting your lunch at least as many times as you got in this thing here? So at least 22 times. So part of the issue I think that comes up with these at least, at most, less than, more than questions is that we know less than, your book has a nice chart on this, by the way, if you haven't looked at it. We know less than means we want smaller things. Oops. We know if you want something that's more than, should be than, sorry, that's going to be bigger stuff. So when we see at least, I think there's a tendency to want at least to act like less, but it doesn't. And I think that throws people off. At least, if you're told at least 22, that means 22 is the least amount you could have. Fair? So if we want at least 22, that's going to be 22 and everything bigger. So out of our 40 days, that 22, if we forget our lunch at least 22 times, that means it's going to be 22 or more times. Is that fair?
Yes, thank you.
Why 22? We were told to find the probability of forgetting our lunch as many times as we answered in part B. So as many times as is unusual. Now, presumably, if 22 times is unusual, forgetting it 22 or more times should also be unusual. So I would expect this probability to be comparatively small. I mean, it looks like a big range from 22 to 40, and it is a big range. But we know that our forgetfulness peaks at about 15.6. So it's those, we're forgetting a lot here. And by the time we get to 9 and 22, we're not forgetting very often. So I would expect this to be fairly small, even though it seems like it's a large group of numbers, a large interval of values. It is by comparison, but it's not numbers, that, not days that we expect to happen very often. So we have a couple of choices for finding probabilities. Eraser's not working. In binomial distributions, we have three tools. Tools for finding probabilities in binomial distributions. Those three tools are: one, a formula; two, your calculators; and three, Excel. Now, there are certainly other softwares other than Excel and other tools other than calculators that will do this, but those are the three big tools that we are using. The formula is that n factorial over x factorial n minus x factorial, probability of success x times probability of failure q, n minus x times. So that's our probability of a particular number of failures. So that was the formula that we built together. The disadvantage of this formula is it's a fair amount of work to calculate. If you're doing it by hand, even if you're doing it by hand, these powers are almost impossible to do by hand. So you're asking the calculator for a lot of help anyway. And it only gives us singular probabilities. So if we tried to use this formula on this problem, we would need to use the formula with the n equals 40, the p equals 0.379, and the x equals, we'd have to do it for x equals 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, all the way up to 40, and add those results together. I don't want to do that. And I don't want you to do that. It's a tremendous amount of work. And we don't have to do it. So we will tend to use this formula fairly inoften. If the numbers are small and we're only looking for 1 or 2 probabilities, it's a nice formula to use without having to bring out the big guns. But more often than not, we'll use the big guns. On the calculator, we have 2 tools. We have one, the binomial PDF tool, and 2, we have the binomial, oh, it doesn't type out the whole word. I think it ends at the M, binom CDF tool. Binom. And both of them have the same coding. Ooh, I believe, I know the N is first. Oh, I just looked this up. Is it N?
How do you find it on the calculator?
We'll look at that in a second.
Okay, thank you.
I think it's NPX. Like, I'm in this order: the number of trials, the probability, and then how many you want. So the big difference between these two, the binomial PDF is just binomial probability distribution function. So that's for one value. The binomial CDF is cumulative probability distribution function. So this is for a bunch of values. So this is one value and everything below it. One value and, I'm going to say down, one value and lower. So again, we could do it for, use the PDF for 22, 23, 24, 25, 26, 27, 28, and add those all together. And this would make that a little bit easier to do, but still annoying to do. Or we could use the CDF to find a group of values. The problem is we want an upper group of values, not a lower group of values. And the CDF, by its nature, and a lot of our tools are going to do this, by its nature, our tools are going to give us from a value and down. So the CDF tool wants to go from a value downward. So if we're going to use that CDF tool here, instead of trying to go from 22 upward, which our tool doesn't do, we're going to go from 21 downward. So that's going to be our binomial CDF. Again, with 40 trials, with our probability of 0.379, and we want 21 and down. Now, 21 and down is not going to give us what we want directly. It'll give us this portion. Let's take a moment and find that. There is a video on your week 5 block on MyOpenMath on using the calculator to find binomial distributions. So I do recommend looking that over if you haven't. But if we wanted to use this here to find it, it is under our distributions, and you have a distribution button here So second distribution will get us to our distribution tools. If we scroll down, we'll see binomial. We want the CDF. Enter. And it's asking us nicely. If we didn't have the nice sub menu, we would just be typing it in. So the sub menu is nice because it tells us what the values stand for. So we want the 40 trials. Our percentage is 0.379. And the value we want is that 21. Now, again, why do we want 21 as opposed to 22? Because I want the 22 to 40 to be what's left. The 0 through 21, we're essentially going to remove by finding its probability. So I don't want to include that 22 because I don't want to remove it. So we're going to paste that to the home screen. Again, if you don't have that sub menu, just type them into the parentheses, the binomial CDF NPX. And that's going to give us our value from 0 to 21. So from 0 to 21 is 0.979. Is that right? 9792. Okay. So I think Olivia, you asked where or how to put that into the machine. Does that work for that part?
Yeah, it does a little bit. Thank you.
Okay. Now, still, we have the trouble that this is what's below what we want. We want this upper piece, not that lower piece. But the probability from 0 to 40 completely has to add up to 1. Remember, all our probabilities have to add up to 1, right? So if we know that this is the lower part and we want the upper part, 1 minus the 0.979 is going to give us what's left. And we could actually have done that in the calculator just by going 1 minus and then bringing in that distribution. Binomial CDF, enter. Still the same values, so I'm just going to go down to paste. So if we look back at this, we'll see the 1 minus binomial EDF, and it will do the subtraction and do it all at once. 0, 2, 0, 0, 2, 0, 7, so 0, 2, 0, 1. So we can have it do it all at once as long as we put in that that 1 minus. If we didn't, if we just were left with this 0.97, so let's say you just did that one and got the 0.97, we can still just go 1 minus second answer, and it will take 1 minus the last answer that was put in there and give us that same value. So if you don't like doing it all at once, totally understandable. Do it in a couple of pieces. And we're going to have to do this 1 minus anytime we want at least, anytime we want more than, anytime we want the upper set, because our tools will always give us the lower set. What we want is, if what we want is the lower set, if what we want is the lower set, then that's what our tools give us, great. If we want the upper set, we got to subtract from 1. So find the probability for getting your lunch at least as many times as was considered unusual, so at least 22 times. The the computer doesn't make you answer these in sentences, but you should really be get used to expressing them in sentences. The probability of forgetting your lunch at least 22 times is 0.021, or if you prefer, 2.1%. Gonna let that kind of gel for a second. Questions on that? No problem. Does that work for you guys? Anything you want to ask about that or add to that? Or now, Excel has these same two tools, essentially. It kind of has them hidden as one tool. It is the binomial, binom.dist, binomial distribution. It has, I think it's XNP, but then either true or false, that's 0 or 1. So if you put a 0 in there, it's going to do the PDF. Or if you type false, it's going to do the PDF. Binomial distribution XNP1 is going to be the same as a PDF. So the 1 says yes, do it cumulative, or you can put it in I'm true. The 0 false, not cumulative, works like the PDF. So it's essentially the same tools. They just look a little bit different. Hopefully the work on your lab helped with that. Ali, you wanted to look at number 8. Oh, 8 would be a good example. So given what we just did, try to write out what your statement would be for these two questions, like whether you want to find the value or not. I mean, if you got your calculator with you, go ahead and find the value. But what would you put into your tools? So I'm going to give you a minute or two to kind of decide how you'd approach it. And Ali, your problem 8 will probably be a little different than this one, but same basic premise. Okay. Before you get too far, the reason I want to stop you before you get too far here is I cannot stress enough how helpful it's going to be to get in the habit, particularly for what's going to happen in chapter 7, of making yourself some sort of little diagram that, from 0 to 8 trials, and even from 0 to 8, it's even not too bad to just label all of those tick marks. But particularly 4 and 7 are the ones we're going to care about. But we could label all of them with not too much trouble. So you can highlight what you're looking at. So at least 4 girls, where on that chart is at least 4 girls? Well, it would include 4. At least 4, if 4 is the least we're allowed to have, at least 4 would be 4 up through 8. So for the question, at least 4 girls, that's the part of the distribution that we want. It can be very surprising how helpful just a little diagram like that can be in trying to set these up. Now this CDF3, CDF3, it's kind of like on that video that I sent out to you guys yesterday. This is just a shorthand I'm writing out. So we're going to do cumulative distribution function at the 3, cumulative distribution function at the 3. We'll certainly need to put in the n, the x, use the whole binomial, when we put it in. So it's just a little way to symbolize it for ourselves. Or for me, you can symbolize it however you want. But we want, again, like the other problem, we want this upper portion. Our tool gives us from values down. So we're essentially thinking about, instead of getting 4, 5, 6, 7, and 8, we're going to take the whole 100% and remove the 3, 2, 1, 0. Because our tool gives us values downward. So it gives us our X and lower. So it's easier to remove those lower ones. We could use PDF at 4 plus PDF at 5 plus PDF at 6 plus PDF at 7 plus PDF at 8, but that's irritating. Don't do that. It would work, but the more numbers you get, the more annoying that is. So we're going to have 1 minus, if we're using the calculator, it's the binomial, the binomial CDF. Our n in this problem is the 8 children. The probability of success is in this case being a girl, so 0.5. And we want the probability of 3 or less because that's what we're subtracting from 1. There are 8 trials. 0.5. Should really be 0.52, by the way. Probability of girls is actually 52% in practice. So 1 minus that CDF 8.53 gives us 63. .63, what was it? Once 4 decimals, 67. Gonna give you another minute or two with the at most sound. But if you have any questions on that, let me know. Allie, does that diagram help with the at least? It's a simple little diagram, but oh, it can make such a huge difference.
Can you hear me okay?
Yeah.
Yeah, it helps a lot.
Yeah. I've had people who just won't draw the diagrams, and they'll come up and ask, when we had classrooms, come up and ask for help. I'll be like, well, draw your diagram. And they go, I don't like diagrams. Go draw your diagram. And they'll come back a couple minutes later, still asking for help in that problem. They haven't drawn a diagram yet. It's like, draw the diagram. I like to just do it. I'm not going to talk to you until you draw a diagram. And they go back and they get all grumpy and they draw a diagram and they go, oh. Particularly in chapter 7. Oh my gosh, it's going to be terrible. Unless you draw diagrams, in which case it'll be nice. I miss classrooms too. So at most 7 girls. So at most 7 means 7 is the most we can have. That's our high end. So at most 7 is from 7 downward. Well, we like that because that's what our tool tries to give us naturally. So from that 7 downward, that's what our tool likes doing. So that's just a cumulative distribution function from 7 down. That's what the job of the cumulative distribution function is. We don't have to mess with it. So it would just be a binomial CDF 8.5 and 7. Now, expectation-wise, do we expect this to be a low probability or a high probability? Now, the probability of having 7 girls out of 8 is low. But remember, we're adding the 7 girls to the 6, to the 5, to the 4, to the 3, to the 1, to the 2, to the 0. At most 7 girls, the only way not to have at most 7 girls is to have all 8 girls. Fair? So this probability should be really high. I wouldn't be surprised if it was more than 90. Tessa, yes, we can and will. So we don't need the 1 minus in this. So I'm going to grab that CDF tool again. We'll tend to use that one more than the PDF, frankly. 8 trials, 0.5. We want 7 or less. The cumulative is the or less. So, yeah, 99.6. Wow, really high. So 0.9961. Also, by the way, just for the fun of it, since the only one left is the 8, we also could have done 1 minus the PDF at 8. That would have given us the same thing and would have been fine. But gosh, since our tool wants to do or less, give it a chance to do its job. But either one would have been perfectly fine. That would have been the same thing. Questions about those? Before we look at the handwritten homework. This is one of those weeks it's nice to have late passes, isn't it? I was worried, I kept getting things like, can you extend this? Can you extend it? And I was like, maybe I should. And then I was like, wait a minute, they all have 5 late passes. If something happens, by the way, and you run out of late passes, let me know. I'll listen to your sob story with an open mind. So is that?
Yeah, I feel like I totally bombed this one.
Was it?
I feel like I totally bombed this handout.
That was a great sob story. I bet you do. I don't think it's as bad as it seems, but it can seem bad. It's a lot of information. It's a lot of values. So let's look at it. A life insurance company sells a big value 1-year term life insurance policy to a 20-year-old male. Why is a 20-year-old male buying a 1-year term life insurance policy? It's a silly thing to do. Anyway, there are reasons, but it's weird. For $350. According to the National Vital Statistics Report, Volume 58, Section 21, these numbers have absolutely nothing to do with the problem whatsoever. They're just the label of where to look in the National Vital Statistics Report. It did make you feel like you were supposed to do something with it, didn't it? The probability that the male survives the year is that much. So that's our probability of survival. Compute and interpret the expected value of the policy. So how much does the policy cost? Well, it costs $350. What's the possible payout? Well, the possible payout is, what is that, $250,000? So, hey, this is worth $250,000. Great. Well, it's only worth $250,000 if you die. Chances are 99 or 0.998734 probability is that you are just going to lose your $350. That's the most likely thing to happen. Fair? So that loss value has a weighted average or weighted probability of 99.8%. But there is a chance that you'll get the $250,000. Of course, you'll still have paid the $350. So absolutely, Alan, we got to subtract that off. But you're only going to get that value for this policy if you die. What's the probability that we're going to die? Well, 376. So fairly small. And this is that, I think this was actually chapter 5, a little bit in 6.1, that general formula for expected value, or the mean of a probability distribution, was the different values multiplied by their probabilities. So the values times their probabilities, all added up. And we looked at some of those in terms of games. So like the 1 out of 6, we'd lose this much. 4 out of 6, we'd lose this much. 1 out of 6, we'd win this much kind of problems. This doesn't feel like gambling as much because it's an insurance policy, but it essentially is gambling. So you multiply that out and you're going to get the expected value of that policy. Fair? As how do approach that problem? Let's see. I think number 2 is similar. Yeah, very similar. An investment counselor wants, calls with a hot stock tip, believes that if the economy remains strong, which is a big if, you'll result in a profit of 50,000. Well, great. If it remains strong. If the economy grows at a moderate pace, the investment profit will be 10,000. Hey, that's still, a good return if we grow at a moderate pace, but the investment will lose $50,000 if the economy goes into recession. So, okay, in one case will make 50,000, in one case will lose 50,000, in another case will gain 10,000. That's more gaining than losing. So this must be a good deal. Well, it depends on what those individual probabilities are, right? If it's very likely we're going to go into recession, then I don't like this deal. If it's very likely that we're going to continue to grow at a high rate, then I do like this deal. So the probabilities take those values and weight them based on their probabilities. So what do we know about the probabilities? Well, we talked to an economist, and the economist says there's a 20% chance that it will remain strong, a 70% chance that it will grow at a moderate rate, and a 10% chance that it will slip into recession. Well, that 10% chance makes me feel a lot better about this. I would like that 20% to be higher, but I can't be too greedy, right? So that 10% should make me feel a little bit better, but how much better? Well, let's compute that expected value. It's essentially that same thing up there. Expected value is the sum of our values times the probability of those individual values. So 50,000 times 20%, because we have a 20% chance of getting this. So essentially we look at, well, what's 20% of that? Plus 10,000, we have a 70% chance of getting that. So let's look at 70% of that. Minus 50,000, we have a 10% chance of losing that. So let's look at a tenth of that. Multiply that out and add it together, and that's going to get our expected return on that investment. Now, I don't know what that is. What is that? 7,000 plus 5,000. Is that 12,000? You guys have calculators. You can tell me. Yeah, thanks, Nick. So yeah, now is 12,000 a fairly good return? Depends on what your investment goals are and all that, and depends on what your risk tolerance is. We only have a 10% chance of that losing, so the risk tolerance is fairly low. But so whether it's good or not depends on how you feel about that. So there's more in consideration than just, is this number positive or negative? But it is strongly on the positive side, so that's at least a point in its favor. Now, remember when we did expected value for binomial distributions, we weren't adding together like this, but remember our expected value for probability distributions, mu, was n times p, right? Essentially, probability distributions only have one thing that happens, so it's only got one piece. It's the same, essentially the same piece. It's just there's only one of them because there's only one of those yeses happening. It's how many yeses happen. Well, what's the probability of that yes happening? So it's actually very similar to our probability distribution expected value. It's just only one term instead of multiple terms. So if that helps you put those two things together. Insomnia is a side effect. It's terrible. So how many would we expect to experience side effects? Well, that's essentially what we just talked about. So this is a binomial distribution. We know that because we're only side effects or not side effects. So that's one big thing to do, and one big point of the latter part of this section is to be able to look at these first these first two problems and go, well, that's not binomial. That's not binomial. Oh, this is binomial. Fair? And oh, it's binomial. So that means we're going to be grabbing these tools, those binomial distribution tools in pink. Is that 0.05% or just 5%? So that's just 5%. So it would be 0.05 as a decimal, but don't put the percent after it if you've already converted it. So careful about that. So our mu, our expected value, is just that NP. So of the 240 people, if 5% of them tend to have a reaction, well, what's 5% of the 240? Was that 12? And 12 people. Thank you, Nick. I think there was a part B for this question. Yeah. Would it be unusual to observe 12 patients? Oh, sorry. Would it be unusual to observe 20 patients experiencing insomnia? Well, the average is 12. 20 is a lot more than 12. But in terms of 240, that doesn't seem like a lot. Depends on how this data is spread out. Do we have a tool for looking at how spread out data is? Wouldn't it be nice if we had some sort of tool for data spread? What tool do we have for data spread that goes along with means and the word unusual? I'm going to keep asking questions in that voice. Standard deviation, absolutely. How do we find that standard deviation? Again, because we're talking about in binomial distributions, population, so we've gone to the Greek. So this is still mean and standard deviation, but because we have the entire population of probabilities, 95% no, 5% yes is the entire population of probabilities. These are mu's and sigmas. We'll use those more as we go along in chapter 8 and 9 especially. We have our formula for standard deviation for a binomial distribution, square root of NPQ. So square root of 240 times 0.05 times 1 minus 0.05, so 0.95. And that's going to give us some standard deviation. Now, I am not going to do that one in my head. Too much for me on a Tuesday or any day, really. But again, you guys have calculators. You want to throw out that number. It's probably around 7. I don't know. What do you got for that value out there?
I got 3.37.
Oh, okay. That's reasonable. I was just guessing somewhere. And out of 2, because remember, this is people, right? So out of, 240 people, those are, say, in the ballpark, right? I shouldn't take wild guesses like that. It makes you guys feel nervous about your numbers when they're off. My fault. So again, that 3.37 people, that's a spread for this 12. Unusual is how many standard deviations? I hear you are shouting 2 in your heads. 2. 3 is almost all. 2 is unusual. Yeah. So 2 times 3.37 people. So 12 plus or minus, 6.74. So 18.74. So what would be unusual? 18 people wouldn't be unusual, but 19 people or more is unusual. We're rounding to the nearest whole number because we're talking about numbers of people. So 18 people wouldn't be unusual. By the time you get 19 people, it would be unusual. So the question, would it be unusual to observe 20 patients experiencing insomnia? Yes, it would. Barely, but yes, it would. If you wanted to do 3 standard deviations, you would say almost all. So if we did another standard deviation, that would be about 22 point something. So about 22 people would be within 3 standard deviations. So 19, 20, 21, 22 would be unusual, but we'd expect all of them to be within, all results to be within 22. So I wouldn't expect any more than 22. It would be unusual to get more than 18, but it happens. So you do want to make that distinction between unusual and almost all. Like, all of us have friends that are a little unusual, right? Unusual people aren't that rare. They're just unusual. So we do want to be careful about that distinction between unusual, almost all, and frankly, even outlier. Tessa, does that help? You were asking about the lab. Sure. And really, it's not or the handed. I don't think this assignment is as bad as it seems, but these problems have just a lot of information, and you're working with a lot of different tools. So it's easy for this to start becoming just, how do I start this? You know, how even do I approach this? And that's one of the reasons that one of the things I want you to start working on, and we'll talk a lot about this in chapter 7, is as soon as we look at a problem, identifying what type of problem is this. 1 and 2 are probability distributions. You're given a bunch of values and their associated probabilities. So it's a probability distribution. Okay, so that means I have these tools. Number 3 is a probability distribution still, but there are only 2 possibilities, so that specifies it as a binomial probability question. That means you have a certain set of tools that apply to it. So starting to look at your problems and start going, okay, what kind of problem is this? So you know which tools to bring to bear is going to be increasingly important. Let's see, Alan, how do we know what goes with what? Economy remains strong. We'll get a profit of 50,000, and the economist says 20% that it will remain strong. So those go together. Growing at a moderate pace, the investment will result in 10,000. 70%, the economy will grow at a moderate pace. So the language kind of tells us which one to put with what, if that helps. Recession, loss, that's why it was negative, and 10% probability that we'll slip into recession. Cool. I tell you, diagrams and colors, man. But that's why, you know, like these others, I didn't really make a chart. This one, I was like, let's make a chart. Let's just keep that organized. You know, I should have made that negative, but. Okay, before I let you go, anything else you guys want to look at? Was this helpful? Do play with these or keep, you know, fussing with these. We will have, as I said, we will work with these more when we get into chapters 8 and 9. But in 8 and 9, we'll be dealing with both these types of problems and our chapter 7 problems, and dealing with both of them in a slightly different way. So being able to tell the difference between which problem we're looking at is going to be really helpful. So you do want to practice these enough to get familiar with them, but hopefully this gives you some more perspective on it to play with. If something else comes up, let me know, and we'll start chapter 7 tomorrow. Have a wonderful day.